The next topic that we're going to deal with is the error probability for M-ary signaling for any general value of M. Previously, we had derived the error probability for the binary case, and we did that for both the unipolar as well as the polar signaling, and eventually we worked out that the polar signaling is better than the unipolar signaling. But nonetheless, in both the cases, we got the expression for the error probability PE as Q function of A by 2 sigma. That's for the binary case. So that's for binary transmission, where that means M equal to 2. We have only two symbols. The symbol is either 0 or a 1. And in the end, we got the error probability given by this expression. And the other difference that you need to notice here is that because each bit is representing a symbol, this symbol error probability is equal to the bit error probability, because in binary transmission, one bit is equal to one symbol. So therefore, the symbol error probability and the bit error probability are identical in this particular case, that is for the binary. Next, we also derive the error probability for the M-ary case with M equal to 4. So we did it for M equal to 4, and we got the expression for the error probability PE as 3 by 2 times the Q function of A by 2 sigma. So that's the final expression we had for M equal to 4. Right? And what we noticed during this derivation proof for the error probability for M-ary transmission with M equal to 4, so that's 4, for M equal to 4, is that when we see these conditional PDFs of the received signal, so the conditional PDF of the received signal Y when M0 is transmitted, so now we have 4 possible symbols because M equal to 4, and the 4 possible symbols could be 0, 0, 0, 1, 1, 0, and 1, 1, which we denote as M0, M1, M2, M3. So now here, one symbol is 2 bits long. So M0 is having 2 bits, M1 is having 2 bits, and so on. So each symbol here is 2 bits of length. So the error probability that we have here is the symbol error probability. Now, what is the bit error probability? We'll come to that later once we have derived the general expression for the error probability for any value of M. Okay, but we are going to use some ideas that we have developed during our analysis for M equal to 4, and that is we notice that the error probability for the two symbols which are at the ends, right? So the extreme left end symbol and the extreme right end symbol, both of them have only one boundary, right? So the boundary for M0 is this on A. So the error happens only if the received signal Y is greater than minus A. And on the other side, there is no boundary. It can go as far as it wants on the left hand side. So this particular symbol on the left, the leftmost symbol, has only one boundary associated with it. Similarly, the rightmost symbol has only one boundary on its left side, and on the right side it has an open space where it can go as far as it wants without having an error. But the symbols which are in between, they have boundaries on either side. For example, this symbol M1 is having a boundary, one boundary to its left and one boundary to its right. So that means if it crosses the boundary on the left side or on the right side, it will cause an error. And based on that, we notice the fact that the symbols on the extremes on the outside have an error probability of Q of A by 2 sigma. So these symbols, so M0 and M3, they both have error probability Q of A by 2 sigma. And the symbols which are in between, which have two boundaries, so they have error probability which is double that of Q of A by 2 sigma. So these have, so M1 and M2, so both these symbols have error probability given by 2 times Q of A by 2 sigma. And then we found the average error probability by taking the average of all of these, okay, assuming equally likely transmission of the symbols, and we got the final answer as 3 by 2, which is 1.5 times q of a by 2 sigma. Now we are going to extend this idea for higher values of m, and then eventually come to the expression for any value of m. And since m is restricted by in its values by that it should be a power of 2, so after 4 the next higher value of m is going to be 8. So when we have 8 symbols being transmitted, each symbol will be 3 bits long. Instead of 0 0, it will be 3 bits long, 0 0 0 0 0 1 0 1 0 and so on. So it's going to be having a length of 3 bits. Each symbol will have a length of 3 bits, but the pattern is going to be the same. So in addition to these 4, we need 8, so there will be 2 more on the right hand side and 2 more on the left hand side. So we'll have the 2 extreme symbols with error probability q of a by 2 sigma, and then in between there will be 6 remaining. So there is a total of 8. So if we remove the two symbols which are at the extremes, in between there will be 6. So each of those 6 symbols will have an error probability of 2 times q of a by 2 sigma, and we are going to use this fact in deriving the expression for the error probability for any value of m. So in general, what we are going to notice is for any value of m, we'll see that the 2 symbols which are at the extreme ends, they will have an error probability of q of a by 2 sigma, and the remaining m minus 2 symbols which are in the middle, those will have an error probability of 2 times q of a by 2 sigma each. So let's see what happens if we have, say, m equal to 8. So when m is equal to 8, so in addition to these 4, we'll have 2 more on the right hand side like this. So we'll have 1 more here. Okay, I'm not going to plot this, so that's 2 here, and similarly we can have 2 more on the left hand side as well. So now that will give us a total of 8 symbols. So 1 2 3 4 5 6 7 and 8. So we can call them as m0 to m7. So this will be the probability of the received signal y given m0 is transmitted, and this will be the probability of y given when m7 is transmitted, right? So in between we have p of y given m1, and this will be p of y given m2, this will be p of y given m3, this will be p of y given m4, p of y given m5, and p of y given m6. Okay, now we don't need to write down the error probabilities for each of them. So what we notice is the error probability for m0 and the error probability for m7, the 2 symbols which are on the extreme ends, the leftmost and the rightmost, they will have an error probability of q function of a by 2 sigma. All the others, pe m1, the error probability for m2, the error probability for m3, and the error probability for m4, and the error probability for m5, as well as the error probability PEM6, right? So the 6 symbols which are in the middle, M1, M2, M3, M4, M5, M6, they will all have 2 boundaries, one on the left hand side and the other on the right hand side. So that's a boundary for this, and that's a boundary. So all these symbols in between have 2 boundaries on either side. and the two extreme symbols, they have only one boundary. The other side is open for them, and all the others, they have two boundaries. So they have error probability which is twice that of the extreme symbols. So that will be 2 times q of a by 2 sigma. So in general, what we're going to observe is, out of the m symbols, so out of m symbols, the two symbols at the extreme ends, symbols at extreme ends have error probability q of a by 2 sigma each. Okay, so there are a total of m symbols. Out of the m, the two symbols at the ends, they have error probability of q of a by 2 sigma. The remaining symbols in the middle is m minus 2, in this case 8 minus 2, which is 6. In general, it's going to be m minus 2. So the remaining m minus 2 symbols, m minus 2 symbols in the middle have error probability 2 times q of a by 2 sigma each. Okay, so we are going to use this fact in finding the average error probability for m, for any value of m. So we have two symbols which will have error probability of q, and in the middle we have m minus 2 symbols with error probability 2q. So with this information, we will now write the expression for the average error probability. So average error probability, and again we are going to assume equally likely symbols. Okay, that means all the m symbols have equal probability of being transmitted. So that means p m0 equals p m1 equals p m2 up to p m minus 1, right? So we start from 0 and go up to m minus 1. 0, 1, 2, 3, 4, 5, 6, 7 in case of 8. In case of 4, it is 0, 1, 2, 3 and so on. So the last one is pm m minus 1. So all of them will have an error probability which is 1 by m. If it is 4, it is 1 by 4. If you have m equal to 8, it's 1 by 8. If it's 16, 1 by 16 and so on. So in general, we can say the average error, the probability of symbol being transmitted when they are equally likely is going to be 1 upon m. And with that information, we can now write the average error probability as 1 by m into, so we have two symbols in the ends which have error probability of q of a by 2 sigma and q of a by 2 sigma. So the extreme left and the extreme right, these symbols have error probability of q of a by 2 sigma. So we add them, and then in the middle we have m minus 2 symbols with 2q. So we have to add the 2q m minus 2 times. So it's basically m minus 2 times 2q. So in between we are going to have plus m minus 2 times 2 times q of a by 2 sigma plus the q of 2 sigma at the last symbol. So that's the leftmost symbol, the m minus 2 symbols in the middle, each having an error probability of 2q, and then the rightmost symbol which has an error probability of q of a by 2 sigma. So that will give us the average error probability, and we just need to simplify this expression now. So that will be, we'll keep the 1 by m as it is. So we're going to have, we can take the q of a by 2 sigma as a common factor, because we have q of a by 2 sigma, q of a by 2 sigma, q of a by 2 sigma. So we'll take that as a common factor outside here. So q of a by 2 sigma is our common factor, and that gets multiplied with it. So we have, that's 1 here, 1 times q of a by 2 sigma. So that's 1 into q of a by 2 sigma is this q of a by 2 sigma, and then this q of a by 2 sigma multiplied by m minus 2 into 2, which is 2 into m minus 2. So plus 2 into m minus 2, plus in the end we have a 1 there. So that is the q of a by 2 sigma term taken as a common factor. So we'll simplify that now. So that will become 1 by m into 2 plus 2m minus 4. So I've just added this 1 and 1. So 1 plus 1 is 2. And I multiplied this 2m minus 4. This whole thing multiplies q of a by 2 sigma. So that is equal to 1 by m. We are just simplifying this expression here so that we can write it as compactly as possible. So 1 by m into 2m minus 2. Minus 4 plus 2 is minus 2. So 2m minus 2 times q of a by 2 sigma. So now what we can do is, we can take this 2 out as a common factor. So that will give us, we take the 2 outside, so 2 by m into, it will become m minus 1. So that's 2m minus 2 into q of a by 2 sigma, which is, again, we can, I'm just going to take this m inside this bracket now. So it'll become m by m minus 1 by m. So m by m is 1. So 2 into m by m is 1 minus 1 by m q of a by 2 sigma. So that will be the final answer. This basically what we've done is we simplified this expression so that we get the m only one time. Okay, we don't want to get the m multiple times, and we want to write this as compactly as possible. So for any value of m, we are going to have the general probability of error for the symbol is going to be 2 into 1 minus 1 by m q of a by 2 sigma. And let's see, verify whether this works, because we've already done the proof for binary and for m equal to 4, and see whether the answers match. For binary, we got the answer as simply q of a by 2 sigma, as we showed in the very first slide. For binary, we had q of a by 2 sigma, and for 4-ary, we got 3 by 2 q of a by 2 sigma. Let's substitute these values, m equal to 2 and m equal to 4, and see if we get the same answers. So for m equal to 2, the error probability is 2 into 1 minus 1 by m, m is 2, q of a by 2 sigma, which is 1 minus half is half, half into 2 is 1, which is simply q of a by 2 sigma. So similarly for m equal to 4, the error probability is going to be 2 into 1 minus 1 by 4 times q of a by 2 sigma, and that will be, so that would be 1 minus 1 by 4 is 3 by 4 into 2. That will give us 3 by 2 times q of a by 2 sigma, right? Which is exactly the same answer we had here for m equal to 4. If you notice, it's 3 by 2 times q of a by 2 sigma, and that's exactly what we get here. So that's the general expression for the symbol error probability for any value of m. So symbol error probability for M-ary transmission. So that will be PE is 2 into 1 minus 1 by M Q of A by 2 sigma. Okay, so that's our general expression for symbol error probability, with which we can find the error probability for any value of M. But notice here, this is the symbol error probability, not the bit error probability. Okay, the next thing we are going to discuss now is how do we determine the bit error probability, and we are going to use some simplifying assumptions to make our analysis easier, and then we will derive the expression for the bit error probability from the symbol error probability based on those assumptions. Okay, so we'll have a relationship between bit error probability and symbol error probability. And by the way, for the binary case, that is for M equal to 2, 1 bit is equal to 1 symbol. So therefore, a symbol and a bit mean the same thing in the case of binary transmission. So therefore, the symbol error probability and the bit error probability are identical. So symbol error probability equal to bit error probability. That means the bit error probability PBE, we are going to call this bit error probability as PBE as compared to the symbol error probability, which is simply PE. So PBE is equal to PE. So they mean the same thing in the case of binary transmission. But for any other higher value of M, for M equal to 4, 8, 16, 32 and so on, then the symbol error probability and bit error probability are two different things. They do not mean the same thing. Let us now develop the arguments to get a relationship between the bit error probability and symbol error probability for any value of M. And for that, we are going to make some assumption, and that would be a reasonable assumption. Bit error probability is what we are interested in finding, because we want to know what is the fraction of bits that are going to be in error if we transmit a sufficiently large number of bits. So we want to find the average error probability for the bits. So in the case of binary, as we said, 1 bit is 1 symbol. In the case of say M equal to 4, then 2 bits equal to 1 symbol. So we have 4 symbols, right? M equal to 4. So the 4 symbols are 0, 0, 0, 1, 1, 0, 1, 1. Now, if we transmit one symbol and that symbol gets corrupted, for example, we transmit M0. Okay, let's name these M0 to M3. Suppose, let's say I transmit M0, but if I receive M0, that means no error. Okay, we transmitted M0, which is 0, 0, and we received M0, which is also 0, 0. So therefore, there is no error. But if we transmit M0, and let's say the receiver decides this as being M1. M1 is 0, 1. So we transmitted 0, 0, but the received sequence is M1, which is 0, 1. So that is one symbol error. Okay, so that constitutes a symbol error. So that's a symbol error. Similarly, if we transmit M0 and if we receive M2, which is 1, 0, that is also a symbol error. And if we receive M3, which is 1, 1, that also constitutes a symbol error. So symbol M0 has been received as M1 or M2 or M3. So that is one symbol error. But what we notice is, when we have a symbol error where M0 became M1 or M0 became M2, in both these cases, the number of bits in error is 1. Out of the 2 bits, only 1 bit is in error. So we had 0, 0. Out of these 2 zeros, the first 0 is still correct. Even though the symbol M0 became M1, the first bit of that symbol is the same as the first bit of the transmitted symbol. So there is only error in the second bit. So I will underline the bit which is having an error. So that's an error. And similarly, when we transmit M0 and M0 becomes M2 at the receiver, we get 1 0, and out of the 1 0, the second 0 is correct. So in the transmitted symbol also we had a 0 in the second place. Here also we have a 0, but only the first bit, which was a 0, has become 1 here. So there is only one error even in this case. And but when you transmit M0, and if that M0 becomes M3, then both the zeros have become 1. So that now constitutes 2 bits of error. Okay, and that is a situation we want to avoid. We want to arrange the symbols in such a way that even if an error happens in the symbol, the error should be in such a way that out of all the bits within that symbol, only one of the bits should be in error, all the others should still be correct. Okay, and we'll arrange the symbols in such a way, and that sort of arrangement is called as gray coded arrangement. So we call this as gray coded arrangement. And so in gray coded arrangement, neighboring symbols differ in only 1 bit position. So we will put 2 symbols next to each other in such a way that they are different in only 1 bit position. All the other bits are same. So if we put M0 and M1 next to each other, and if M0 becomes M1, then even though it's one symbol error, it will be only 1 bit error, because out of the 2 bits, one of the bits is still correct. Similarly, if we have M2 next to M1, if the symbol M0 becomes M2, we will still have only 1 bit error. But if we have M3 next to M0, then M0 becoming M3 will make the entire symbol to be lost, because both the bits in that symbol would have changed, and both the bits would be in error. So we want to avoid that situation, and to avoid that, we arrange the symbols in this what is called as the gray coded arrangement, such that the neighboring symbols are different in only 1 bit position. Once we have such an arrangement, then there is a high probability that if an error happens, then it would have only 1 bit error in 1 symbol error. So 1 symbol error would correspond to only 1 bit error. But very rarely the case where 1 symbol error is more than 1 bit error can happen. That will be a rarity. Okay, it will be a very rare case. That means it will have a very small probability of that happening. So we want to arrange the symbols in this gray coded fashion. So in gray coded arrangement, we are going to place neighboring symbols in such a way that they are differing in only 1 bit position. So let's take the example of m equal to 4, where we had the 4 symbols M0, M1, M2 and M3. So that's P of y given M0, and that is P of y given M1, P of y given M2, and P of y given M3. Now we could arrange them as, say, 0 0, 0 1, 1 0, 1 1. Now if you look at this arrangement, the symbols 0 0 and 0 1, the symbols which are next to each other, they are different in only 1 bit position. So the first bit is 0 in both the cases, only the second bit is different. And similarly, if you look at these two, then we see that the first bit is same, only the second bit is different. The second bit is here 0 and 1 here. But if you look at the middle ones, which have two boundaries, right? So if this middle one goes to that side, it will become an error. This one comes to this side, it's also an error. So if these two get interchanged, that means if we transmit M1 and if we receive it as M2, then both the bits will be in error. 0 1 will become 1 0. So the first bit is 0 here, it's become 1 here, and the second bit is 1 here, that's become 0 here. So both the bits will become error. So we want to avoid this situation, so we make the arrangement in a slightly different way, so that the symbols are not having two positions different which are next to each other. So, or let me rephrase that sentence. The symbols which are next to each other should be different in only one bit position. So we'll have, let's say this as 0 0, and this we can have as 0 1 or 1 0, no problem. Let's say we have this as 0 1, and the next one, instead of 1 0, we can make it 1 1. So now between the second and third one, the difference is only in one position. So the first bit is 0, the first bit is 1. So only the first bit is different. The second bit in both the cases is same. Similarly, for between the first and the second, the first bit is same, only the second bit is different. So there is a difference in only one position. And now in the last one, we can make it as 1 0. So we have just interchanged this 1 0 and 1 1. And now we see that all symbols which are next to each other are different in only one position. So between the third and the fourth, the first bit is same for both, only the second bit is different. So such an arrangement is called as gray-coded arrangement. And what happens when we have such an arrangement is that each symbol is more likely to be pushed into the neighboring symbol because of noise. So when there is an error, the received signal Y may cross the threshold and go into the neighboring symbol space. So M0, even when there is an error in M0, most of the times it will become M1. And that way what will happen is, even if that's a symbol error, at least some part of the bits will still be correct. So not all the bits of M0 will be lost. Some part of the bit, only except for one bit, all the other bits will be correct if we have such an arrangement. Now for M0 to become M2, right, which is far away, that means it needs a much bigger noise. So a bigger disturbance of noise will cause the M0 to go to M2, in which case 0 0 will become 1 1 and both the bits will be having an error. So similarly, for M1 to become M0, it should have a large amount of noise to push it far enough into the region of M0. So that is a rare case, and that will happen only when the noise is very, very strong. Most of the times, the average noise would be only to push the symbol into the neighboring symbol space. And in that case, except one bit, all the other bits would be recovered correctly. So with the gray-coded arrangement, what we can say is that most of the time, one symbol error would correspond to only one bit error. So if we say M0 became M1, there will be error in only one of the bits. All the other bits would be correct. So we are going to use that fact to make our relationship between the symbol error probability and the bit error probability. So with gray coded arrangement, one symbol error would translate to one bit error. So except for one bit, all the other bits, even in the wrong symbol, would still be correct. Okay, it will be a very rare case that both or all the bits will get corrupted, or more than one bit will get corrupted, and that will happen only when the noise is large. Okay, and with that we can now have a relationship between the bit error probability and the symbol error probability. And to understand that clearly, I'm going to use an example of the number of a certain number of symbols being transmitted. So suppose let's say we are transmitting 100 symbols. Okay, suppose 100 symbols are transmitted. Out of the 100 symbols that are being transmitted, 10 symbols have error. So the probability of symbol error in this case, probability of symbol error PE. So let me write that clear. Symbol error probability, which is PE, is going to be 10 out of 100 symbols. We are not even using the expression now for the error probability. We are just using the basic concept of probability. So out of 100, 10 are in error. So the probability of error is 10 by 100. So that's our symbol error probability. Now we know that with the gray coded arrangement, one symbol error means 1 bit error. So 10 symbol error means 10 bit errors, right? So therefore, if we have 10 symbol error, that corresponds to 10 bits in error. Now let's take the case of m equal to 4. In m equal to 4, one symbol is equal to 2 bits. So if we have transmitted 100 symbols and each symbol is 2 bits long, that means we have transmitted a total of 200 bits, right? So number of bits transmitted, number of bits transmitted is equal to 200. So out of the 200 bits that have been transmitted, there are 10 bits in error. So we transmitted 100 symbols with m equal to 4. So each symbol is 2 bits long. So we have transmitted a total of 200 bits. Out of the 100 symbols, 10 symbols have error. And since in the gray coded arrangement, one symbol error means 1 bit error with high probability. So that corresponds to 10 symbols in error, meaning 10 bits in error. So out of the 200 bits that have been transmitted, 10 bits have error. So the probability of bit error, which we will now write it as bit error probability as PBE, is 10 bits out of 200 bits have error. And we can rewrite that slightly differently as 10 by 2 into 100. Now what is this 10 by 100 that we have here? The 10 by 100 is the same here, which is the symbol error probability. And what is the 2 here? 2 here is the number of bits per symbol, which is nothing but logarithm to the base 2 4, right? In general, logarithm to the base 2 m for any m, right? So what we have here, this, I'm going to circle this 10 by 100. This is the symbol error probability, and this 2 here is nothing but logarithm to the base 2 m. So the bit error probability can be written in terms of the symbol error probability PBE as PE divided by logarithm to the base 2 m. Now this equal to that we have put here, I'm going to replace that with an approximation, approximately equal to. The reason is because although with the gray coded arrangement, there is a high chance that each symbol gets mapped onto a neighboring symbol, and that means one symbol error will lead to only 1 bit error. It does not exclude the chance of more than 1 bit error. There might be an occasional symbol which is affected by a large noise, a large amount of noise, which causes more than 1 bit error. For example, M0 may become M2, but that will happen very less frequently. It has a low probability of M0 becoming M2 or M1 becoming M3. Most of the times the symbol will get mapped. If you transmit M0, it is more often than not, if it has an error, it will become M1. So if you transmit M1, most likely it will become either M0 or M2, but very rarely it will become M3. But that rare chance is still there, okay, although it is not going to be frequent, but occasionally it can happen. And in such a case, we have to take that into account. So because it's a rare case and the chance of that occurring is very, very small, we say the symbol error bit error probability is approximately equal to the symbol error probability by log 2m. So we put this approximately equal to sign because we want to take into consideration that sometimes, very rarely though, there might be a symbol which has more than one bit error. So one symbol error may be having more than one bit error, but that is a very rare chance. So most of the times it will be one symbol error equal to one bit error. So therefore we have this relationship between the bit error probability and symbol error probability. So the general expression is given by this relationship for bit error probability and symbol error probability, or the relationship between these two terms. And generally the symbol error probability will be equal to the bit error probability for m equal to 2. So when we have a binary case, when m is equal to 2, PBE will be PE by logarithm to the base 2, which is 1. The denominator will become 1. So PBE will become equal to PE, which is basically saying that the bit error probability is equal to the symbol error probability for the binary case, because in the binary case each symbol is representing each bit. So one symbol is equal to one bit, or that means the bit and symbol are identical representations. They mean the same thing in the binary case. Okay, but in general you will see that the bit error probability, because for m greater than 2, you see that the bit error probability is lower than the symbol error probability because it is getting divided by a number greater than 1, right? And just to illustrate this even further, let's do one more example with m equal to m equal to 8, and again try to establish this relationship. So we will use the same setting that 100 symbols are transmitted, and out of the 100, 10 symbols have errors, and we will use m equal to 8. So if 100 symbols are transmitted with m equal to 8, one symbol is equal to 3 bits, which is logarithm to the base 2 8, right? That is 3, which is nothing but logarithm to the base 2 m. That's the general expression for the number of bits per symbol. So the number of bits transmitted, is going to be 100 symbols into each symbol is 3 bits, so we have transmitted 300 bits. And there are errors in 10 symbols, so one symbol error corresponds to 1 bit error most of the times, right? Very rarely it can have more than 1 bit error. So because that's a rarity, we just say approximately one symbol error is going to be 1 bit error. So if we have 10 symbols in error, that means 10 bits in error. That corresponds to 10 bits having error. So the bit error probability now will become which we denote as PBE, is the number of bits in error is 10, the number of bits transmitted is 300, which we will simply break it down as 10 by 3 into 100, and 10 by 100 is the symbol error probability, so that here is the symbol error probability PE. So that is PE by 3 is nothing but logarithm to the base 2 8. Logarithm to the base 2 8. So we have the same relationship again. this one symbol error is 1 bit error. That is approximately correct. Occasionally, one symbol error may be more than 1 bit error, but approximately this is the relationship when we have a gray coded arrangement for the symbols. So we have the general expression for the bit error probability PBE as approximately equal to the symbol error probability by logarithm to the base 2 n. Okay, we'll stop here for this lecture and we'll continue with the next topic. In the next lecture we will talk about a specific form of filtering for the receiver, and then we will also discuss about how to compute the error probabilities and the bit rate for communication under various settings. And then we'll see what is the trade-off between the bit rate and the error probability. What we'll notice is that if we try to increase the speed of communication, that is, if we increase the bit rate, the error probability increases. So therefore, in order to deal with that error probability and to keep the error probability as low as possible, we have to use several techniques in a communication system. So increasing the data rate, increasing the speed of communication is not as straightforward a process. It involves a lot of engineering techniques to be applied, so that while we want the bit rate or the data rate to be high, at the same time we want the error probability to be low. There would be no point if we transmit very fast and most of the bits that we transmit have errors. They'll become useless. So we want to ensure that the communication is fast as well as reliable. That means free of errors. Okay, so we will discuss about the trade-off between error probability and bit rate in the next lecture.